Thanks for organizing this this workshop at the end of the Evoclearn project. And I would like to take the chance to briefly review what has happened in the core of VocalTractLab during the project, what is happening, and what are the plans for the foreseeable future. And the goal of all the developments here are, of course, to improve the models, to improve the realism, but also to reduce complexity of the models, and in the end, to improve the naturalness of the synthesis. So let's have a look at the VocalTractLab pipeline here. So maybe I can first say that during the first year of the project, I put in a lot of effort to bring the software to a new level where it's very useful and quite stable for the developments in the Evoclearn project. And that was then the basis, for all the studies that were made here, or for most of the studies that were made in Evoclearn. And in the remaining 2 years, there also happened a few things, which will then, be part of a new version 2.4 is at some time in the future. So, but the version 2.3 was released about 2 years ago. And this is a pipeline for this version. And it has different levels of control, which are shown here. And the highest level of control is the one at the left end, where we can input a sequence of pitch targets into the synthesizer that we see here, and a sequence of phonemes and their durations. And that is also a new feature in the version 2.3, but that is not really used in this project, so I won't go into detail about that. From the sequence of pitch targets and the sequence of phonemes, we can then generate gestural scores, from which we can then obtain sequences of vocal tract model parameters and vocal fold model parameters. Yeah, and these are all different levels of control. So the highest level, the phone sequences, then the level of the gestural scores, another possibility to control the synthesizer. And the next level is to specify directly the trajectories of the vocal tract and vocal fold model parameters. The vocal fold and vocal tract model have been revised prior to the version 2.3, and I will talk briefly about that. And from these two models, so according to the pipeline, we generate a time-varying tube model of the vocal system. And that is then transformed into an aerodynamic acoustic model of the vocal tract and a network circuit model. And that can then generate the speech audio signal. Yeah, so this is basically the pipeline. And one thing that was included in the version 2.3 is a new geometric vocal fold model. Previously, we mainly used a self-oscillating model of the vocal folds, the bar mass model, but it turned out that it's quite hard to control under different aerodynamic conditions that can be in the vocal tract. So the aerodynamics always have quite a big effect on what actually happens in the larynx. And this geometric model is easier to control. It's based on a model by Tietze from 1984. And we can see here the parameters of the model, F0, lung pressure, then the rest displacement at the lower and upper end of the vocal folds, at the posterior end. Then we have a constant posterior chink area that we can specify, a phase delay phi between the upper and lower oscillation at the upper and lower edges, and a relative oscillation amplitude, which is interesting to specify four-voiced fricatives, for example, where the oscillation amplitude is lower. And then we have three new components here, which are interesting for making more realistic oscillations. And that is a degree of double pulsing, so that can give us or generate us a rough voice. We can see it here in the bottom right corner. This double pulsing it can make that we have a big oscillation and a smaller oscillation, and that repeats periodically, and that gives us a rough voice, which is often found also in natural voices. So this can be specified. Then we have a pulse skewness parameter, which is new, and the effect can be seen in the middle picture at the bottom. So the opening and closing is not symmetric here, but it is slightly skewed either to the right or to the left. And we also found that a little skewness towards the right side makes the voice more natural. And then we have a flutter parameter, which simply defines some pseudo-random fluctuations of F0, which are superimposed on the specified F0 contour or pitch contour, that are defined by the pitch targets. Okay, so this is one of the models that has been included, and the other one is the VocalTract model, where I could reduce the number of parameters from 22 or 3, I think, to 19. And from these 19 parameters, 2 are actually can be derived from the others. So here TRX and TRY, the 2 with the star here, they are dependent on the other VocalTract parameters, can be inferred automatically, so that we have, in fact, only 17 parameters to control or to specify the whole VocalTract shape here. There were some simplifications that really had an effect also on naturalness, positive effect, but I will not go into detail. But in effect, this is much more simpler than the VocalTract model from version 2.2. Yeah, another thing that we looked at or studied are 3 components that are normally not included in acoustic simulations of the vocal system in other articulatory synthesizers. So this is now the aerodynamic and acoustic side of the simulation. And the 3 components that we looked at are the effect of the piriform fossae. So these are the dashed boxes here in the middle. We looked at sound radiation from the neck skin to produce a voice bar during voiced plosives. And we also implemented transvelar coupling or a transvelar coupling filter that allows the coupling of sound from the oral cavity through the closed velum into the nasal cavity. So with this transvelar coupling filter, we can also have an acoustic excitation of the nasal cavity. Also, the velopharyngeal port is closed. And that is claimed to be one of the mechanisms that generates a voice bar, even if there is no actual, even if the oral cavity is closed and also the velopharyngeal port. So we generated sentences by including these additional components or not including them, and asked the listeners, what do you prefer, what sounds better? And it turns out that all 3 components do not improve the naturalness. So this had no effect on the naturalness, but it obviously improves the realism because it makes the simulation more realistic. So we suspect that it's simply these components discriminate different speakers. Yes, some speakers may have a bigger piriform fossae, others have a smaller side cavity here. Some people have stronger transvelar coupling, others have less. So I think it's more the thing that discriminates speakers, but it's not really necessary for a natural sounding speech. Okay. So let's look at current research and what will come in the future. So what I just presented, that is already all in the version 2.3 and the basis of the Evoclearn studies. What's new is a more realistic model for the radiation characteristic. So to briefly explain, normally, the radiation characteristic, that is a transfer function from the volume velocity in the plane of the lips to the sound pressure at the ear of the listener. And normally this radiation is modeled in very simple terms by just a point source. It's like a very tiny sphere that is pulsating sinusoidally, increasing and decreasing its volume, and that radiates sound into all directions. And this model is normally used to model sound radiation from the lips of a speaker. And this is obviously not very accurate because it omits all the effects of the head and the torso. Yeah, so we have no diffraction on the head, on the torso, and so on. But it is very simple. It's essentially this transfer function is essentially a high-pass filter, first-order high-pass filter, with a rise of 6 decibels per octave. And that corresponds to the first derivative in the time domain of the generated volume velocity. So it's very easy to compute. So a more realistic model that was often proposed, but has not really been implemented in any of the simulations that I know, is the model of a pulsating piston in a sphere. So this is more realistic, one could say, because here this big sphere is the head, and the piston represents the oscillation of sound in the plane of the lips. And then we have diffraction around the head, diffraction effects, and that gives us a different transfer function. And we also compared this with an even more sophisticated model, and that is this 3D model of a speaker, where we really simulated the whole acoustic field around the speaker with torso and with the head using a finite element simulation. And when we look at the simulated transfer functions for these cases, they look like this. So the simple model here at the left side, this acoustic monopole, this has a dashed line characteristic as a spectrum. The piston in the sphere has a characteristic that we see here as a solid lines above the dashed line on the left side. So that means we have an emphasis of the high frequency component compared to the low frequency components. Yeah, so it's a stronger rise if you want than the 6 dB per octave characteristic. And when we look at a realistic radiation, then we see it's actually much more complicated than the piston in the sphere. So we have the solid line here in the right bottom picture, which has dips and maximum minima, and they come from the reflections from the torso mostly. Yeah, so this quite complicated pattern. And so we have also compared these acoustically. We generated sentences with all these 3 different characteristics and had people compare these sentences in terms of naturalness, also in combination with different voice qualities. And it turned out it doesn't have a positive effect on the naturalness. So it doesn't really matter. So the simple model is good enough. When you compensate its lack of realism with your voice source, because the LTAS, the long-term average spectrum, is determined by a combination of the voice source and the radiation characteristic. When you have a more realistic radiation characteristic, as here for the right case at the right side, then you can make a more realistic voice source model. You don't have to compensate for deficits in the radiation model with your voice source. So that is our conclusion, and there is a paper submitted about that. Okay, let's look at the losses. So one problem that I found is that the bandwidth of the formants tend to be too small in the acoustic simulation in VocalTractLab. And that is essentially the same for all other vocal tract simulations in other synthesizers. And the problem is why is this and what can we do about it? Yeah, so the loss mechanisms need to be revisited. And there are 2 approaches for this, or two things that we look at the moment. And one suspicion is that the losses in the model or the simulation are too low because the simulation models don't consider the notches of the lips. Yeah, when you see this simplified 3D printed vocal tract resonators here, we made them with notched lips with different notch depths. Yeah, and normally when you simulate radiation, you don't simulate these notches. You just simulate radiation from a tube that is a straight cut at the anterior end. And this is not really the case. When you have notched lips, the sound also escapes, sound intensity or sound energy also escapes to the side of these notches, and that can be expected to increase the bandwidth. And indeed, it is like that. So when we use these models with different notch depths and compare their bandwidth, then we see here in the figure on the right that the bandwidth is indeed increasing, and not only because the resonances shift towards a higher frequency with increasing notch depths, but also above this effect. Yeah, which you can see here. No? So here the blue and the pink curve, these are notch depths of 3 and 4 centimeters. And we have significantly higher bandwidth here. Okay, but this is just one example. We tested that for many different models. Okay, another loss mechanism that needs more research is the loss due to the soft walls. And for this, we examined or we created physical models with hard plastic walls, like these gray models here in the top picture, and then also models with soft silicone walls that we see here as these white silicone models. And we have this method to accurately measure their transfer functions. And we can see the gray curves are the silicone models here, and the black curves are the hard-walled models, that the soft walls shift the first resonance toward a higher frequency, and at the same time significantly increase the bandwidth. So this means we have stronger losses. And we also see that without the soft walls, we underestimate the bandwidth up to 2 kilohertz. So we need to properly include this loss to get realistic bandwidth here. So this gray area that I show here, that these are measurements from human subjects. Yeah, this area, and we are below that with our black dots here. Okay, and yeah, this is actually the shift of the first resonance, which is shown in this figure. And it's also quite significant. And this shift is stronger for resonances that have a lower frequency. So when we have in the hard-walled model resonance frequency of, let's say, 200 or 250 hertz, the soft walls increase it by 150 hertz. So that is about 70 or 80%. That is quite significant. But we will look more closely into this phenomenon and also then adjust the model parameters in VocalTractLab to account for this more properly than at the moment. Okay, and finally, what's planned next is that we make new speaker models for 2 additional men and 2 additional women. We already have the ethics approval for this study. We already recorded the data of 2 male speakers. And I hope in the second half of this year, we will also record the MRI data of 2 women. So from each person, we need about 60 3D MRI scans. And this can then be used along with acoustic data from these speakers to create additional speaker models. And then when we have 5 of them in total, we can really produce a whole variety of speaker characteristics by the weighted superposition of these 5 different models. And this will give us a big variety of speakers, so we can generate a whole population, if you want, with different weighting factors. Okay, that's it. Thank you for your attention.